Hi, my name is Claudio Tag and I work in the Enterprise Containers team at IBM. In this demo, we'll analyze different use cases concerning the use of API management together with integration services running on AppConnect Enterprise and a service mesh called Istio. In particular, we will focus on containerizing the integration platform using Istio for service discovery and microservices connectivity, using header mapping for A/B testing and canary deployments, and we'll have a look at the differences between an API management solution like IBM API Connect and a service mesh like Istio. Finally, we will have a look at securing the Istio mesh. Before we jump into the scenarios, let's have a look at understanding the Istio architectural components and resources that we've used for this demonstration. First of all, we are running on an IBM Cloud private Kubernetes cluster, and we are deploying our applications into a specific application namespace. In that namespace, I have an application A, which runs a microservice, in this case just a single container, which is exposed through a Kubernetes service. When enabling Istio for the cluster, Istio components like Mixer, Pilot, Citadel, and Galley get deployed to a dedicated Istio namespace called Istio System. In addition to that, an Istio Ingress Gateway and an Istio Egress Gateway get deployed to the same namespace. Enabling a namespace for Istio means activating Istio injection. That essentially means that for each pod into the Istio-enabled namespace, a sidecar container will be deployed side to side with the microservice container in the pod. In the same Istio-enabled namespace, an object referencing the Istio Ingress Gateway gets created, and the same happens for the Egress Gateway. At namespace level, an Istio policy, which defines the security and the access modes within the mesh, for example mutual TLS, gets created. For each application, we create a virtual service, which is the way of accessing the application from outside the mesh. Virtual services can have specific destination rules associated with the Kubernetes services which they will be invoking. Finally, the Istio Egress also has its virtual services and destination rules associated with it in order to connect to hosts external to the mesh. If I create a second microservice for my application, that will also have a sidecar and a Kubernetes service which exposes the microservice out of the pod. I can then create a destination rule that links the virtual service onto the specific Kubernetes service within the application. And this way, from the ingress, I can connect to the different versions of the microservice application through the virtual service routed by the destination rule on the specific Kubernetes service which exposes that pod. In the same namespace, I can have another application with its own virtual service and destination rule or destination rules to expose the container out of the mesh. In the first use case, we will use AppConnect Enterprise in containers to decentralize our integration platform. We will also explore the ACE dashboard for a DevOps-centric approach to integration. In my ACE dashboard, I can see 3 different AppConnect servers running across my Kubernetes cluster. Each of them has got a different number of replicas, which are the number of pods in each deployment. And opening the servers allows me to see the applications or flows that are running on that server. I can have a look at the properties for that particular flow and the version of the AppConnect Enterprise server running that particular flow. The idea of decentralized integration is that each server will be able to run a separate application that can be controlled and managed in a fine-grained way. However, the dashboard allows me to extract that information from all the servers and shows me the integrations and applications running across the different containers. The dashboard also includes a content server in which I can store the different bar files that I have deployed or that I'm ready to deploy. I can pick an undeployed bar file and kickstart a deployment into a new containerized ACE server. This brings me to the Helm chart. I can choose the specific version that I want to deploy and provide the required information. In this case, the name of the Helm release and the namespace where I want the service to be deployed. Required parameters for the Helm chart are the node port to which the server is going to be exposed and a link to the content server onto the ACE dashboard, so that the ACE application gets pulled every time a container gets restarted. We can choose if we want a local queue manager to be installed in the containers, and also assign a number of replicas for the pods in that deployment, in this case 4. Other parameters include the version of the ACE container, and a choice around creating persistent volumes if we want the state of the ACE container to be statefully persisted. As mentioned, the deployment will be exposed via node port, and in case we selected a queue manager, we could give a queue manager a name at this stage. Once I've reviewed all the parameters, I'm ready to deploy the Helm chart. This takes me to the Helm release, where I can review the 4 deployments being currently stood up. Back to the ACE dashboard, I can see the server coming up and the number of replicas coming online. In a few seconds, all 4 containers in the pods will be up and running. This is reflected in both the Helm chart deployment, but also in the ACE dashboard. If I click on my new server, I will see the bar file that I've selected being deployed, together with the FlowDaddy packages. I can have a look at its properties, and also the eSQL file contained in the bar. I will now simulate a failure in a pod to show Kubernetes self-healing capabilities. I will manually remove a pod, which will go immediately in terminating state. And in a few milliseconds, a new container is spun up to replace the one that I've just removed, bringing the replica count back to 4. The dashboard also provides me with logging and monitoring capabilities to extract information from containers should they disappear for any failure. A Kibana dashboard is provided in order for me to analyze the logs coming from the server I've just deployed. I can see that in the last few minutes, logs have been pumped out the containers and collected through the Elasticsearch Logstash and Kibana stack, which is now displaying those. A Grafana dashboard is also available to display data collected through a Prometheus data collection queue. This gives me information around memory and CPU utilization by containers deployed to the clusters. I can go and select the server that I've just created and see a spike in CPU and memory consumption, given by the fact that the container was started. I can also select the different pods making up my deployment, including the one that was replaced when I simulated the failure into one of the pods. In the second use case, we will use an Istio service mesh to enable integration between 2 containerized services. One is an ACE server, and the other one is an internal system of record. Istio will enable the communication between the 2 containerized services using sidecars and mutual TLS, and also expose the ACE service outside of the mesh using an ingress. The endpoint is exposed to an external API Connect developer portal, which I can use to pull the API. I can select a test client and provide the required variables to the API call. This will invoke the service exposed through the Istio ingress, which calls a flow onto the ACE server, which integrates to the backend service into a container. All of that done through Istio sidecars. The API response gives me a 200 code for success, brings back information from the backend systems, and also provides a timestamp, the name of the containerized ACE server, and the name of the backend system, including its version. Through a Grafana dashboard, I can have a look at the traffic hitting the Istio ingress and going through the mesh. In particular, I can see that the traffic is secured using mutual TLS across the entire mesh, from the local server to the backend containerized system of record. I can also generate additional traffic and see the effects on the Grafana dashboard. We are now going to extend this use case by adding a second version of the same ACE microservice. In this case, whilst the first version points at the internal system of record, the second version, v2, will go out of the mesh using an Istio egress and connect to a DataPower gateway which connects to an external system of record. Whilst normal traffic will continue to flow to version 1, we will use header mapping and Istio routing to allow testers to hit version 2. Here I can see version 1 and version 2 side to side. On the left-hand side, normal traffic is flowing through version 1 of the ACE service via the Istio ingress. On the right-hand side, no traffic is currently hitting version 2. This test harness is currently pointing at the endpoint exposed via the Istio ingress. By making an API request, I can hit version 1 of the service, which is connected to the internal system of record. We have configured a destination rule in Istio, which looks for particular value of headers in order to direct calls to version 2. If I set the header to the value test, the API request will end up this time on version 2 of the service, which is connected to the external DataPower gateway. I can see that reflected in the dashboard. Whilst normal traffic hits version 1, testers can have a look at version 2, which is hitting a different endpoint, but also secured within the mesh using mutual TLS. Removing the test header from the API call brings me back to version 1. Through the Istio Grafana dashboards, I can see where traffic is being directed based on Istio header mapping. In the fourth use case, we will expose the API to an external API gateway using API Connect, and we will run a canary test using Istio for traffic management. In the Schiali dashboard, I can see the Istio ingress being connected to the two versions of the ACE service, one that connects to the local system of record, and the other one that connects to the external DataPower. In API Connect, I have created an assembly which calls the target endpoint and maps the response from the ACE service into a simpler response. In particular, looking for data from the backend system, and information around the ACE server which we are connected to. I can hit the API directly from the API designer. And get a response which highlights the data from the backend systems, as well as the name of the backend system and the version of the ACE service I have just invoked. The traffic is also being detected by Schiali, which highlights that I'm currently hitting version 1 and the internal system of record. Back to the API designer, I will now create a load of traffic against the API endpoint. Here I can see the 1000 invocations being kick-started and hitting version 1 as expected. The traffic flow within the mesh is detected and displayed on the Schiali dashboard. From my Cloud Private dashboard, I can now modify configuration parameters for Istio in order to influence the destination rules. In particular, I've packaged into this Helm chart a set of information that can be edited. By doing an in-place upgrade of the Helm chart to its same version, I can go and change those parameters. I will leave the Istio label and the mutual TLS the same, but I can change the weight between the two versions, directing now 90% of the traffic to version 1 and 10% of the traffic to version 2. This is done whilst I'm simulating traffic against the API management live. I will submit the changes and go back to the API manager, where I will start seeing v2 as a response through the API proxy, only for a small number of occurrences. In the traffic management dashboard, I can see some of the traffic being directed to v2 and average out around 10% in the past minute or so, exactly like my destination rules dictated. If developers are satisfied with the quality of version 2, they can now split the traffic 50-50 across the two different releases. This can be done again by editing the destination rules weight. External traffic will start to be equally distributed between version 1 and version 2 of the ACE service, as also shown by the Chiali dashboard. After a short period, the dashboard averages out around 50% traffic splitting. The side-to-side Grafana dashboards show me how traffic was originally only directed on version 1, then 10% started hitting version 2, and now traffic is equally distributed between the two versions. More information can be provided at API level from the AppConnect Analytics dashboards, like status code of the response in the past 15 minutes, and response time, minimum, average, and maximum. Also number of API calls per day. I can go back in time and look at the same information across the past week. I would see more error codes coming from the APIs, and a much larger number of total API calls. In the fifth use case, we will have two different ACE services which point at two different endpoints based on a plan in API Connect. External users will subscribe to a plan and will be directed to the correct ACE service based on the plan itself. Our application consists of two different versions of the ACE server, one that is specific to Swindon users and one that is for everyone else. In API Connect, we've created a product which points to this API and two plans associated with that product, one for Swindon and one for everything else. In the Swindon plan, we've also implemented rate limiting at 100 calls per minute. In the other plan, we've limited the number of calls to 3 per minute. Let's go and have a look at the API itself. Selecting the latest version will bring me to the assembly diagram, in which I will see the same API that we've used before, proxying and mapping the result out, with an additional policy to set a variable which grabs the name of the plan and maps it into the header, which will in turn be used by Istio for traffic routing. As a developer, I can access the developer portal and select which API and product I want to use. I will select the Geo product, which includes two APIs and two plans. Each of the plans will have a rate limiting per minute associated with it. I can also have a look at the comments made by other developers. I will select the latest version of the API and test it directly from the developer portal. Using the client that is subscribed to the Swindon plan, I can invoke the API with the correct variable and get a response which points at the service that is specific for Swindon and the backend system which is connected to that service. In this case, the DataPower gateway. Still, from the developer portal, I can hit the API a number of times and see that each invocation contributes to the rate count. Traffic from the Swindon plan is reliably hitting the DataPower gateway in the backend. By selecting a different client, this one subscribed to the other plan for different users, the API result will display a service that is generic for the UK and a backend system which is my internal system of record. If I continue to invoke the API, I will see the number of remaining calls reducing, and when I reach 3 calls per minute, the API manager will stop the invocation of that API for rate limit being exceeded. Traffic subscribed to the Everything Else plan is reliably being routed to the internal system of record. In the Analytics dashboard, I can see the different status codes for traffic limiting exceeded, as well as the different type of errors coming from the API response. As usual, I can analyze the response time of the API and the number of total API calls and calls per day. Additional analytics information is provided around the usage of the developer catalog, what are the top products used by developers and the top APIs within those products, and the usage of the portal. For example, success and failure rates, and data usage in terms of traffic. More specific details around products can also be provided. What are the apps that subscribe to products? And what are the plans that those clients use? In the 6th use case, we will use a JWT token from DataPower to secure the Istio mesh, which uses API Connect as the ingress. We will use a different test application, which is the Istio book info example for the purposes of this scenario. In API Connect, we've created an API which invokes the book info example at its endpoint. A token gets generated by DataPower and passed into the authorization header of the book info API invocation. In my Istio service mesh, I have created a security policy which is specific to JWT tokens. This policy dictates that any request coming from the ingress and directed to book info needs to have a JWT token. The issue of that JWT token needs to be DataPower. The location of that DataPower is in a container in the Kubernetes cluster itself. This URI specifies where DataPower exposes its public keys. This effectively creates a DataPower trusted mesh. When invoking the book info service from outside the mesh, we will have to go through DataPower, which will give us access to the secured mesh via the JWT token. Once we're in the mesh, Istio will take care of the routing. From a test client, we can invoke the API using DataPower as the issuer of the JWT token. When the API is invoked, a response comes back based on the Istio destination rules. The entire invocation is secured end-to-end by the DataPower token. In the Istio Grafana dashboards, we can see requests being routed to the 2 different versions of book info across the secured mesh. In this video, we've analyzed scenarios around the usage of API Connect, AppConnect Enterprise, and Istio, focusing on DevOps for containerized integration servers, service discovery using Istio, A/B testing and canary deployments, use of API Connect together with Istio, and finally securing the mesh using DataPower. In another video, we will treat the use cases for multi-clusters, seeing how Istio can provide a multi-cluster mesh and how multi-cluster management capabilities can be used to manage applications and application components across clusters. Thanks for watching.